Did it start? Yes. Quick recap for those of you who just started our video. So we're looking at curve sketching, and we talked about graphing something like a parabola from before. If you had to graph that using previous knowledge, you had to use completing the square, which we did in the blue. But if you use calculus, you can find the derivative, set the derivative equal to 0, because the tangent at any vertex will be perfectly flat, and then you can solve for the x-coordinate of your vertex in a lot easier way than you could otherwise. And so we're going to find out how we can use all the slopes to help us figure this out. All right, so we're on the second one. If f prime of x was bigger than 0, what does that mean? The slope is positive. If your slope is positive, okay, I'll pick a point on here, right here. I draw a tangent to that point on the graph. That's the part where the slope is positive. What does that mean for my graph? Can you see that any of these points right up to this one, right? If I draw another one here, it'll have a positive slope. If I draw another one here, it'll have a positive slope. Any of those places right up to the maximum where the slope is 0 would all have a positive slope. What does that refer to on our graph? The graph is going up towards the maximum. So we would say when the slopes are positive, your graph is increasing. And whenever we're talking about increasing, we're talking about going from left to right. What happens if the slope is negative? We can find that on our graph. I'll do it with purple lines anywhere in this section. And it would be decreasing all the way to that minimum. So when the slope is negative, the graph is decreasing. So one of the things that we're going to do, for example, this cubic graph, if we had it, you would first find out what are the x values, and I'll do it with the red dots. We're going to have two x values where it's equal to 0. And we know that those x values will either be maximums or minimums. Then we will check each section and find out, in this first section, in the green section, all my derivatives were bigger than 0. All my derivatives, my slopes, were positive in this section, which means the graph is increasing, and we'll show that with a little arrow. Then in the purple section, all the derivatives were negative. We're going to show that with an arrow that it's decreasing. And finally, if we did the last section, you would see that it's increasing again. So you'll be able to draw the curve, because you can draw your maxes and minimums and then draw a smooth curve going through. And the only thing that's really helping us draw the curve is the derivative. The derivative finds our max and mins, and the derivative tells us which way it's going. So we already looked at this and said that f prime of x was 6x plus 12, setting it equal to 0, and solving gave us x equals negative 2. If I drew a number line and included negative 2 as my minimum, you can find the point on the graph for that vertex by plugging negative 2 into the original equation. What's happening before negative 2? If you look at your derivative and you choose any number less than negative 2, say negative 4, can you see that if I plug in negative 4 for x, that I will get a negative number? That in this section, f prime of x will be less than 0, which means my graph is going down or decreasing. And if I plug in any number bigger than negative 2, say 0, say 15, say 1,000, plugging that in, can you see that you will get a positive number? That your derivative will always be bigger than 0 in that section, which means your graph is increasing. So when you go to graph this, and this is kind of funny because you know how to graph parabolas, you would say, oh, I know that my vertex is down here at negative 2, comma, negative 13. And I know my graph is decreasing and then increasing afterwards. So this is my final graph. Well, you knew that already because you knew parabolas either opened up or opened down. So once you had the vertex, you would have been able to draw it using your previous knowledge as well. But this is showing us how the calculus can tell us which direction it's going. Because we're going to get into some graphs where we're not quite sure if it's increasing or decreasing or what that looks like. So that's part one, increasing and decreasing. Right? If it is going up from left to right, we are going to define that as increasing. And if it is going down from left to right, we're going to call that decreasing. Good? So on this little graph, we are going to label the max and minimum points in green. There's a green dot. There's a green dot. We're going to show increasing in blue and decreasing in red. So we would say this graph is increasing from here to here because it's going up, and it's also increasing in this section. But this section in between the graph is going down from left to right, so that section we would say is decreasing. And if we pick random points in those sections, right? If I pick a random point there, and I drew my tangent, it has a positive slope. If I pick a random point anywhere in the red section, and I draw the tangent, it has a negative slope. And so the slopes of the lines will always tell us if things are increasing or decreasing. So what we just did on that graph with the tangents was showing this. If you draw a tangent line where it's increasing, your tangent line will always have a positive slope. And if you draw a tangent on the graph where it's decreasing, your tangent will always have a negative slope. And when it's equal to 0, it's always going to be flat, which means it's either a maximum or a minimum. Okay? There are some points on graphs that don't have tangents. And there are also sometimes points on graphs where it gets flat, but it's not a maximum or a minimum. I will show you a graph that you know. Okay? X cubed. Okay? Now, Most likely when you draw your x cubed graph, you draw it a little bit bad from grade 12. That's your x cubed graph. Okay? It actually, at this point here, if you draw a tangent line, is the weirdest tangent line that exists ever. Because it goes right through your graph, and you feel like tangents shouldn't be able to cut through a graph, but they do at that point. If you look at the derivative, right? The derivative is 3x squared. And if you set the derivative equal to 0 and try to solve for x using all your complicated techniques, you get x equals 0, which coincides with this point 0, comma 0. And so the tangent at 0, comma 0 is flat. And it cuts through your graph. Right. I can cut through the graph at this point, only at one point, but that's not a tangent. All tangents touch a graph once. Touches the graph only once. But this line touches the graph only once, but it's not a tangent. Right? Yes. So tangents usually don't cut through a graph. Yeah. So this is kind of a weird tangent because it does cut through the graph at that one point. Y equals 3 is flat. So it's a maximum and a minimum. Maximum. Okay. So we call any place where the derivative is equal to 0 a stationary point. And there's 3 kinds of stationary points: maximums, minimums, and the one on the x cubed graph is called a stationary point of inflection. Whew. Next, we find some very important numbers which we call critical numbers for curve sketching. Critical numbers for curve sketching are any places where the derivative is equal to 0, and any places where there are non-permissible values on f of x or f prime of x. The helpful making connections? I will quickly solve this making connections. So when you solved inequalities such as that, you first solved where, I'll just show you, okay? If I want to solve where y is greater than x squared minus 10x plus 21, I first set it equal to 0. Okay, set it equal to 0. This can factor nicely, x minus 7, x minus 3. So it's equal to 0 when x is 7 and x is 3. And in grade 11, when you solved this, you then made a number line, and you plugged in 3 and 7. Do you remember doing open circles at 3 and 7 because there was no equal sign? And you fill circles when you did. Some people are nodding a little bit. Not covered in French. It's probably because the numbers 3 and 7 don't translate well. Anyways. Yeah. Okay. Next, in the inequality, you were trying to solve where y was bigger than. So you do a check. If I plug in something between 3 and 7, like 5, does it work? Well, 5 minus 7 is negative 2. 5 minus 3 is 2. 2 times negative 2 is negative 4. Is negative 4, right, is 0 greater than negative 4? That section was true. Okay? Oh, or do I got them mixed up here? It seems, no, it's not quite true. So, but, okay. What we're trying to find out, and what you would have done in grade 11, is set some of these sections off as true and false. Between 3 and 7, if I choose 5, I get a negative number. I know, but this is not, see, here's your 3 and 7. Those are your x-intercepts. Your parabola is opening up. The parts where this is true are this section is bigger than this section. So, or wait. Yeah, something is going wrong in my brain right here. But what you would have done in grade 11 is you would have found out where sections were true and where sections were false. That wasn't part of your curriculum. Okay. Well, this is what it looks like for us in calculus. We use that same idea as a number line. So the idea of drawing a number line and putting critical values on it is what happens also in calculus. So in this situation, what you're looking at, and I realize what was different in that last question, but we won't worry about it right now. In this one, y equals 2x squared plus x minus 21. You could complete the square to graph this, but we're going to use calculus. The derivative is 4x plus 1. Setting that equal to 0 and solving tells us that we have a critical point when x is equal to negative 1/4. In fact, that's where our vertex is going to be. Our vertex is going to be at negative 1/4, comma something. How would you solve that? You'd plug in negative 1/4. Anybody have really happy math skills right now? You want to do that mental math? 1/8 minus 1/4 is negative 1/8 minus that. Negative 21.125? Maybe. Okay, so we have our vertex. According to calculus, we then make a number line with our critical point, which is negative 1/4. And we check values before and after in our derivative. And we're trying to find out, is our derivative positive or negative in each of these sections? So you plug in, what's a number less than negative 1/4? Any number. Negative 2/4. Okay? Thanks for choosing a beautiful negative fraction for mental math. What would be easier to use if you didn't want to use a fraction? Negative 1. Plug in negative 1 for x. Negative 3 is your answer. All you need to know, you don't even need to know anything other than, is it positive or is it negative? It's going to be negative. So I'm going to put a negative sign in here, and anytime your slopes are negative, your graph is decreasing. Plug something in bigger than negative 1/4. You wanted to say 1. Yeah, of course you would want to say negative 1/8. No, Let's do positive 1 or 0. Right? Plug in positive 1 into your derivative. You're going to get a positive number. This section is positive. Anytime your derivatives are positive, your graph is increasing. So we know that we have the point -1/4, -21.125. That number has not been verified. But your graph is going down until it reaches that point, and then it goes up afterwards. And it's a parabola, and we knew this was its shape, but this is calculus telling us that it's that shape. But some of these ones aren't the most fun to do completing the square. So calculus telling us 14x minus 14, set it equal to 0. Because when the slope is 0, you're going to have a max or a minimum. Solving this is pretty easy. X is equal to 1. So we now know our vertex is at 1 comma something. In this case, plugging in 1 isn't as bad as last time. We get -4. Then according to calculus, we make a number line. We put all of our critical points, which include everywhere where the derivative is 0 and any non-permissible values. But this graph has no non-permissible values, so the only critical point is at 1. Plug in something less than 1 into your derivative. Plug in 0. Question? So it's always the x value. Okay? The x value is what your critical point is. And then to get your actual y coordinate, I just plug 1 into my original equation. So if I plug in 0, something less than 1, I get a negative number. So I would just show that this section is negative. And what does that mean? It means my derivative, my original equation has to be decreasing since my derivatives are negative. And plugging something bigger than 1, like a billion, okay, it's positive, means that it's increasing. Yeah, 14 times a billion. Okay, thanks. I was working in your head. And then minus 14, which rounds to 14 billion. Right? And so we can draw our graph. We know our vertex is at 1, -4. And again, it is decreasing and then increasing afterwards. Okay, one that you may not remember as well. Do you remember what the 1 over x squared graph looks like? Okay, perfect. No, they're a little bit different. So, okay, we'll see. So first of all, if I was doing the derivative, I would set it up and look like this. If you make that equal to 0 and solve, what happens? You get, what did you do? Did you multiply both sides by x cubed? And then you got 0 equals -2? Wonderful. That's what you did. Oh my goodness. This is problematic. No solution. Can't be 0. Okay? So it has no solution. So there are no places. This graph has no maximums, no minimums. Okay? What do we also know about this graph? It has a non-permissible value, though. That x can't equal 0, and that's true for the derivative as well, that x can't equal 0. So when we go to our number line, we only have one critical point, which is 0. What happens when you plug something into your derivative that's less than 0? It goes positive. So this graph is increasing before 0. And what happens when you plug in something larger than 0? It is negative, so then it is decreasing. Now, this appears to show that the graph should have a maximum. Can you see that? You would think that it should have a maximum. But that's a non-permissible value. What do non-permissible values look like on graphs? Asymptotes. So we have an asymptote at x equals 0. Do you remember your other skills in asymptotes? What happens when there is a bigger degree on the bottom? You have a vertical asymptote. You'll have a vertical asymptote at y equals 0. Now we have to draw increasing, then decreasing. And there's only one way to do that. This is the only option for increasing. Otherwise, if you went to your asymptote, you'd have to go down. And on this side, the only option for decreasing would look like that. So we just used calculus to draw something that you would have used other skills in grade 12 or grade 11 to do. This is in the grade 11 curriculum that everybody during the pandemic skipped. And this is in the grade 12 curriculum, and it's usually the last unit. So if you're currently in the grade 12, I don't know if you're on the last unit yet, probably not. Not quite. You're working, people, they tend to work towards that unit. Okay. What about 1 over x cubed? Similar to the last graph. Non-permissible value, x can't equal 0. So on our graph, we know that we're going to have an asymptote here at x equals 0. We're also going to have an asymptote here at y equals 0. If we want to find out how it's going to look in that section, well, your derivative I think in calculus, the negative exponent rule comes up more than it has ever before. You use it a lot in calculus. So we got negative 3 over x to the 4. Again, if we set this equal to 0, there's no solution to that. But if you draw your number line with the only critical point being the non-permissible value of 0, and you plug in anything less than 0, can you see that the answer will be negative? So it needs to be decreasing. Because negative 3 over x to the 4 will be negative if you plug in anything. And it will also be negative and decreasing in that section. Given your asymptotes, can you see that the only way you can draw decreasing twice is there and there. And now we're going to, like, the parabolas, they're really kind of disappointing to draw with calculus because you already know how to draw parabolas. Like, finding the vertex so much easier, maybe a nice application for calculus, but after that you're like, I know how to draw a parabola, okay? But when we get to this graph, we can now graph this better than you could graph this in grade 12 pre-calculus. In grade 12 pre-calculus, you graphed some of these, but you had a little bit of, well, you haven't yet, but you will. All you would have known from grade 12 pre-calculus is that this is an x to the 4 graph. X to the 4 graphs are similar to parabolas in that they either look like this, but might have some crazy stuff happen in between, or they go down, but at the end they're either both opening up or opening down, just like a parabola, because it's an even exponent. This one opens up, but it might have something like that in the middle, but we don't know. How do we find that out? How does calculus help us? Well, big question mark. The derivative would be 4x cubed minus 16x. We could set it equal to 0. And notice that you could factor out a common factor of 4x, leaving you with x squared minus 4. This could factor even further because it's a difference of squares. And there's 3 places where it's equal to 0, at 0, at -2, and at 2. There's no non-permissible values, but we have 3 places where the derivative is equal to 0. So when we draw our number line, we would put in -2, 0, and 2. I often like to use the factored part to figure out where it's increasing and decreasing. Because you don't need to find the actual number. For example, plug in something less than -2. -5. Okay? What's 4 times -5? A negative number. What's -5 plus 2? A negative number. What's -5 minus 2? A negative number. If each of those 3 factors are negative, and I multiply them together, a negative number times a negative number times a negative number, I'm going to get a negative number. And if my derivative is negative, that means my function is decreasing. Which makes sense, right? It should be going down until it hits the minimum. In between -2 and 0, if I choose -1, 4 times -1, still negative. But -1 plus 2, that would be positive. -1 minus 2 is still negative. A negative times a positive times a negative is positive. This section of my graph should be increasing. If I plug in something between 0 and 2, like +1, can you see this will be positive? This will be positive. This will still be negative, making this section negative, decreasing again. And finally, if I plug in something bigger than 2, like 10, all of those numbers would be positive, meaning that your function is increasing again. So we use the number line. We're going to get that W, like we predicted. But now when we go to graph it, these three critical points, if we want to find out what they actually are, they're not hard to find these actual points. Plug in 0 into the original equation. Can you see that you would get -3? Plug in -2 into the original equation. 16 minus 32 is -16 minus 3, -19. Plug in +2. 16 minus 32 minus 3, -19. What does my graph look like? It decreases, increases, decreases, increases. And we have a graph that's more accurate than we could graph using our grade 12 pre-calculus. In grade 12 pre-calculus, when we graphed this, the only thing you were able to find were these points, your x-intercepts, if possible, and that its end behavior looked like this. And the rest you were just told, just estimate what you think it would look like. Not necessarily. Yeah, but you can have an x to the 4 graph that doesn't have all three of those bumps. We will graph some x to the 4 graphs that go like that flatten, but don't have an extra bump. They have sort of like an x cubed kind of thing happening in the middle. We can have some x to the 4 graphs that are just like super flat, like parabola that's extra squished out. Right? So, and we're going to see all of those. This one happens to be the perfect W, but we can't say that for sure. All right. I will end video 1 here.